Sorry, folks. All right, if you're just joining us, we've been fighting all day with trying to get the PowerPoint to open, and PowerPoint won't open today. This one is a PowerPoint, but the one on the DVD will not open, and the one on Blackboard won't open. So what we're going to have to do, where we left off last time, any questions on anything we've done so far? Okay, we're in Chapter 6, which is Electricity and Magnetism. We're on page 145. We're talking about electrostatic forces, and example 6.2 was where we left off. All right. Electrons carry a negative electric charge and revolve around the nucleus of the atom, which carries a positive electric charge from the proton. That should be protons. I don't know why it just says proton. The electron is held in orbit by the force of electrical attraction at a typical distance of 1.00 times 10 to the negative 10 meters. Okay? So that's your distance. Let me get my pen set up. Okay. So the distance is a pretty small number. 1.00 times 10 to the negative 10 meters. Okay? Incredibly small distance. It says, what is the force of electrical attraction between the electron and the proton? Well, here's your formula for the force, electrostatic force. And this, by the way, is Coulomb's law. We just did it at the end of the class last time. The F is equal to K, that's Coulomb's constant, also called the electrostatic constant, times Q1 times Q2 divided by D squared. There's our D. We're going to square that. It's going to get even smaller. Okay? Now, Coulomb's constant is 9.00 times 10 to the pretty big number here, 10 to the 9th Newton meter squared per Coulomb squared. That's a capital C Coulomb squared. Okay? That's your K. The charge on a Coulomb is, both the electron and the proton, is 1.60 times 10 to the incredibly small number, negative 19 coulombs. That's the charge on a proton. It is also the charge on an electron, 1.60 times 10 to the minus 19 coulombs, divided by the D squared, which is 1.00 times 10. Now, I'm going to go on and square this. When you square an exponential, you double the exponent. That's to the negative 20, and that will be meters squared. Okay? All right, too many parentheses all over the place here. All right, this is going to give you the force. Okay? Notice here, the meter square cancels out. The coulomb times coulomb is coulomb squared. Those cancel out. And now you got to pull out your calculators, and might be a good idea to practice this because you might see some one or two calculation problems on a test, just in case. So it's 9.00. You don't have to put in the 0.00. 9 EE or EXP 9. That's what you enter here. Times 1.6. You don't need that extra zero there. EE or EXP negative 19. Now, if you do the negative on your calculator, be sure you use the negative sign in parentheses, not the subtraction key, the one in parentheses. Minus 19 times 1.6 EE or EXP minus 19, and divide by 1 EE or EXP negative 20. Okay? Yes?
Negative 10.
No, you squared it, and that made it negative 20. Just explained that a little bit ago. Okay? Because I did the D squared. Okay? Now, because I took that number and squared it. All right. Anyone punch that in and see what you get? How many newtons? just to give you a ballpark figure, you see this minus 20 and minus 19, that'll be a minus 1 down here. That would make it a minus 20. Multiplied by 9, that makes it a minus 11. So you figure it's going to be something around minus 11. As it turns out, the one they have in the book actually, whoa, not quite minus 11, minus 8. Okay? And the reason for that is this is awfully close to minus 1 times 10 to the 10th. So that would give you one more back. Those two multiplied together will give you, my goodness. Oh, I did this one backwards. Because this is in the denominator, this will be this divided with this, a minus 1 down here. That makes that a minus 18. That makes this a minus 9. And then since that's so close, you do get minus 8. And they get in the text 2.30. Has anyone gotten this yet? Times 10 to the minus 8 newtons. Now that doesn't seem like a lot. But when you figure out the distance that you're talking about is so incredibly small. Okay? Let's just get an idea of what that is. Okay? I don't have a dime on me today, but I have a penny. Okay? So, 10 to the minus 3 meters would be about the thickness of a dime. Not much more, less than the thickness of a penny. Okay? That's 10 to the minus 3 meters. If you took that and sliced that penny into 10 million slices, okay, equal slices, if you can even imagine it, that's the distance you're talking about. So incredibly small, it's just unbelievable, okay? And that small of a force across that, that's going to be pretty significant. So it is a pretty strong force, believe it or not, okay? So about 2.3 times 10 to the minus 8 newtons. All right. Now, what I want to do is try one more time, just to see if this might open. I don't think it will, but it's starting. Hey, look at that. All of the color came. That's a positive sign. Not these colors, though. So it's not such a positive sign. And I'm scared to click on it too soon because it seems like that screws it up. Whatever it was doing before, there they came now. Let's see if maybe it'll open this time. And down here in the corner, that is what this looks like, the first slide looks like. So it is acknowledging it's there. It is a big file, 4.5. Okay. Why do they want me to cancel opening the document? It can't open this type of file. That is ridiculous. Because it says, PowerPoint can't open this type of file, Chapter 6 PPT. That is a PowerPoint suffix. Okay, PPT is. So why it says it can't open it. Now let's see what showing help will do. I haven't done that yet, but let's see. Okay. Let's minimize this. And there's Melanie. We're having computer problems today. PowerPoint won't open a PowerPoint file. It's crazy. So, okay. Well, we'll just continue. All right. Let's look at force fields. Sorry you can't see it. But all of you have the PowerPoint slides on your blackboard. Hopefully your computers will open them. We'll just have to have audio with not much video today. Okay? The next topic in here is force fields. Okay. Now, let's say we turn on the light switch. The instant we turn that on, does that mean that the electrons standing at the light switch are ready to race down the wires and go through the tubes and light us up? Thoughts on it? Yes or no?
Yeah.
Okay. Problem is no. Okay, because two reasons. Yeah, I know. That's what I wanted. Okay. Here's the issue. Electrons travel amazingly slowly. Okay. It would take hours for them to go down the wire and go through all the light tubes, and finally they'd all come on. Okay. Now that's one issue. The second issue is this is alternating current. Electrons, all they do is travel back and forth, back and forth, back and forth. They don't ever go down the wire at all. Okay? So, what is it that makes the lights come on when you hit the light switch? It's the field, not the electrons. The electric field is set up at almost the speed of light. Not quite, but close to it. The field is put into place. And here's what's happening. When you hit the switch, the field is set up throughout the system, throughout the whole circuit. Okay? And the field that's on the electrons right on one side of the switch, that field is also hit at that instant. The electrons that are in the wires right overhead, and the ones here and here. The field hits everywhere almost instantaneous. And that's why the light comes on. Because it's the field that makes it come on, not the electrons themselves. Sure, the electrons are moving. That's the charges.
Electron field.
The electric field. The electric field. Okay? It's not the actual movement of electrons. Yeah, and the thing is, the electrons are moving, and they have the energy, but the field is set up instantaneously. You don't wait for the electrons to travel down the wire. The field is almost instantaneous. A better example would be the automobile. What kind of current do you have in an automobile? AC or DC? DC, because it's coming off of batteries. And now the electrons are moving through the wires. And they're moving incredibly slowly. I think there'll be an example later in the thing. To get from the battery to the tail light would take about 5 hours for the electrons to move that, because they bump into things and stuff. It's an incredibly slow process. But the field is set up instantaneously.
Well, you can change it with an alternator to AC current.
Okay, what the alternator does is change. What you have is a generator in your car that's turning all the time, and the alternator changes that AC to DC, because the generator produces alternating current.
AC to AC.
Yeah, it's AC to DC, because that's what recharges the battery. If you just use alternating current, it would charge, recharge, 60 times a second.
The light bulbs in the tail light
are DC. DC.
Wrong.
Everything is DC except going from the alternator. Well, from the generator that's in your car. They don't call it a generator, do they? But it really is. Do they actually call it a generator?
GM patented alternator So everybody else has to use generator.
Oh, I see. Okay. But it is a generator. It's just called an alternator. Okay.
Well, I think the generators went out in the 50s.
That was Stephen, right? Okay.
Yeah, go down to side generator.
Okay. All right. So it's the field that sets up the that makes things happen. Okay. Now there are a few names in this section: Michael Faraday and James Maxwell. Okay. Michael Faraday was a pretty old man by the time Maxwell was born. Okay. Like maybe, well, not too old. 40 years old, so they overlap maybe a little bit. But Michael Faraday did some of the early work with fields, and Maxwell actually described it. Now, James Maxwell, if you ever see his middle name, is C-L-E-R-K. It looks like it's clerk, but he was Scottish, and Scottish pronounce things all sorts of weird ways, and it's pronounced Clark. James Clark Maxwell came up with 4 equations. You may have had more at one time. He's condensed them down to 4 equations called Maxwell's equations. And those 4 equations basically mathematically model what's going on with electromagnetism. They relate electricity with magnetism, and those 4 equations do it all. No one could verify these until about 70 years after his death, when we finally had enough technology to test the thing, and found out that those equations work perfectly. So he nailed it. Without ever being able to verify it, he nailed it perfectly mathematically. A great example of a mathematical model. Okay? But anyway, they describe the fields. Okay? The charge produces a force field. So anytime you have a charge, okay, let's just have one up here. Positive or negative? You tell me. Which one you want? Positive. Positive charge here. It's sending out a field all around it, 3-dimensional, all around it, and that field, and here's the convention. The lines of force, which aren't really lines, they're sort of curved, but you imagine them, they go outward, away from a positive charge, always toward a negative charge. Always. Okay? So, these rays are emitting outward from this positive charge. Now let's have another charge over here. What do you want it to be? Positive or negative? Doesn't matter. What do you want it to be? Negative. So it's a negative. So now it's trying to get lines of force coming in, and it has a field around it. Okay? And now those field lines are going toward, because the field lines always go away from positive charges toward negative charges. So this field line from here, and this one is sort of sucking in field lines. This is emanating. That's why positive and negative charges attract each other, because the field lines are pulling them toward each other. You have to exert a force to keep them from colliding with each other. Okay? Now, if they're far enough apart, they won't collide, but they still will sense, depending on how far away they are, by Coulomb's law that we just used in the previous example. Okay? Now, if this was a positive charge over here and a positive charge here, now the force lines are going out from both of them, and they're fighting against each other and pushing each other away. And that's why like charges repel each other. Okay? Unlike charges attract, like charges repel. I wish we had the slides. Here's a graph that illustrates this. Now, for people at home, they can't see this because it's that. This is a positive charge here, a negative charge there. These force lines always emanating away from a positive charge toward a negative charge. These are pulling these charges together. Whereas the positive and positive here, they're going out from the positive charge, out from the positive charge. They're pushing each other away. The force lines actually bend to keep from crossing each other, because these field lines never cross. They may connect and pull together, or they may bend and act like a spring, pushing each other apart. That illustrates what's happening in a field. Okay? And the instant you hit that switch, the field throughout the circuit is almost instantaneously done. Yes? We're on page 146. 146. Okay? It's a force field, and it's often called an electric field. Now, there are equations and formulas that go with that. This book does not bother to give them to you, which is kind of a good thing because they're sort of a pain in the neck to deal with. If you think back to the gravity, gravity is a field, okay? The Earth is pulling us toward it, okay? Pulling the moon toward it, okay? Pulling satellites toward it. Fortunately, if they have enough speed perpendicular to that pull, that's what keeps them in an orbit. In a sense, they're always falling to Earth, but because they have a perpendicular component of velocity that keeps them crashing into the Earth. If that were ever to slow down so it wouldn't have enough speed, then it would spiral down and crash into the Earth. And that has happened before. The first, I guess it was the first U.S. space station. I don't know if it got hit by a piece of space junk or just didn't have enough up to keep it going, but for some reason it did crash into the sea near Australia. I don't think any of it hit land, but a little bit of it may have because it broke apart when it came into the atmosphere. And that's going to happen to every satellite we have around the Earth, man-made satellite.
It's been too long ago that they were really concerned about some Russian space coming down.
Yeah, because that was called Soyuz. Was that the one? The old Russian space station. It's had rough days. A cargo ship crashed into it at one time.
Did it come down?
I don't know if it did or not. Does anyone recall? It seems like it did crash, but I can't say for certain. But all of them, they're going to hit something at some time in their life, slow them down, that'll be enough, and then they'll start spiraling in toward the surface. I just don't know if the Soyuz has done it yet or not. I know our first space station did. The International Space Station still out there doing its job, and it's being manned by Russians and Americans and others. And by the way, the Hubble Space Telescope still out there doing its job. However, they've got plans to launch another one to replace it. All right. So, just a couple more issues on this. I was talking about gravitational field. That's like an electromagnetic field with a couple of minor differences. Okay, one difference: two masses always can attract each other. Always. Two charges may attract or repel, depending on if they're same sign or opposite sign. But you see, masses only have one sign, the mass. Okay, it doesn't ever have an antimass. Now, there is a thing in physics called antimatter. Yeah, we're not going to get into that now. Okay. There are actually three models for explaining how gravitational, electrical, and magnetic fields operate at a distance. Now, your slideshow didn't go into this, but I'll mention it because it's in the book. The first is the action at a distance model, recognizes that masses are attracted gravitationally, electric charges and magnetic poles attract and repel each other through space. But it gives no further explanation of why that happens. The second of these is the field model. That's the one we're talking about now. The field considers to be a condition of space around a mass, around a charge, around a magnet, and the properties of the fields are described by the field lines. Okay? And then there's the field particle model, a complex and highly mathematical explanation of attractive and repulsive forces. And I'm not even going to get into that. They talk about virtual photons, gravitons, strong nuclear forces, gluons. The book doesn't give enough explanation, and I'm not about to try to explain that because I don't know enough about it too. Okay? But let's move on to the next topic, which is electric potential. Okay, so far, we started today, we had already started on electrostatic forces. Let me get my pen back. Okay, electrostatic forces. Don't you wish you had PowerPoint? Okay, my writing stinks. And that was basically Coulomb's law. That the force of attraction or repulsion is the Coulomb's constant, K, electrostatic constant, big old number too, 9 times 10 to the 9th, isn't it? Something like that. Yeah, 9 times 10 to the 9th. We won't go into the rest of it. But Q1, Q2 over D squared, where D is the distance between them, squared. Okay? Then we talked about electric fields. And that's what actually the thing that makes electricity work is a field. Fields always go away from positive charge. They emanate away from a positive charge, and they always emanate toward a negative charge. Okay, that's electric fields. And then the last thing that we were talking about was, and that's also called force fields, electric fields. The next thing we go to is electric potential. And this is what we'll be dealing with in some way in today's lab. Okay? Now, electric potential is kind of short for electric potential energy. Okay? It's not quite the same as electric potential energy, but it's very closely related to it. Okay? Remember, these fields are at a distance. So if you have this positive charge up here, that's what you have to have. Say, way out here somewhere, we have a small, very small positive test charge. Okay, the potential is how strongly that field is felt over that distance. Okay, and we've been talking about fields and distances and stuff. It's the potential energy that feels from that charge there. Okay, just like I hold the book into the air here, gravitational potential, mgh, is going to be pulling it down. Okay? If that was a negative charge up here, and that's a small positive test charge, its potential energy is going to pull it toward that. If it's a positive charge up here, it's going to be pushing away from it. That's the difference between gravity and electric fields. Electric fields can go either direction. Gravity is always attractive. Okay? So, in either case, the electric potential energy is changed. If you move a particle into a field or out of a field, you're changing the potential energy between them. What we're interested in is not necessarily the potential energy, but the potential difference. Okay? Now, really, when you remember we were doing our experiments with potential energy and kinetic energy, the pendulum, remember that? Really what we're interested in there was the potential difference. Remember we had the delta H, the difference in height. That gave us a difference in potential energy. So really all along, when we were talking about potential energies, you're really more interested in potential difference than you are the actual amount of potential energy you have. What is the difference between the two states? Okay? Now this is getting very close to what we're going to be talking about. Okay? And you use it all the time and you don't realize probably that's what you're doing. Okay? What is energy measured in? What is the unit that we usually measure energy in? A joule, exactly. Now, there's Peyton, right? Yes. And also Mac. And Chase, right? And Colton, is it Colton? No. Yeah. Is this Colton? Is this Colton?
Taylor.
Taylor. Okay. And Chase, no. Chase? Yeah, okay, I thought so. Yeah, I know you're in here. There you are. All right. Anybody whose name I didn't call? Okay, I got all of you here. So basically, we're only missing Michael, Colton, Tyler, and Zachary, and Raina. Okay. All right. By the way, for those who just came in, PowerPoint will not work today. We've tried and tried and tried. So I'm having to just do it all on. This is PowerPoint, but it's not the slides. So if you go back and read pull up the slides that are on Blackboard, you might be able to relate what we're talking about here. This will be on YouTube. That will not be. I cannot get it to work. Okay, potential energy is measured in coulombs then. Okay? So, what we have is the potential energy from this charge up here, positive or negative charge, whatever it happens to be. We have a small positive test charge here. Okay? So the amount of energy that field's coming from this, from the field, electric field around that charge up there, per unit charge here, that's your potential difference. And does anyone know what we call that potential difference? Which is joules per coulomb. You all know the unit. You probably just didn't realize that's what you're talking about. Volt. That's what a volt is a joule per coulomb. The amount of potential energy felt per unit of charge. Okay? So your electric potential difference, which is in the volts, okay, is your work or energy, the work it takes to move that charge into that field or pull it away from the field, the work per unit charge. So that would be, now here's the strange things, folks. This is the parametric equation. Voltage is equal to, or potential difference equal to work per unit charge. If we put the units down here, the unit for potential difference is also volt, capital V, is equal to joule per coulomb. Okay? Now, both of these, the name of the unit, volt, and the name of the parameter, voltage, or potential difference, we use the symbol V. The unit for that voltage is V, volt. Both named after Alessandro Volta, another person you could maybe choose to write on if you chose to. Joule, you could have chosen him. He's the one that came up with energy measurements. So that's what work is measured by, is in joules, and charge is measured in coulombs. And there's a Charles Coulomb, a French physicist, did a lot of the early work with electricity. So Volta was Italian. We've already lost enough time today. I won't go into that story, but anyway. So that's what a volt is 1 joule of work or energy per unit charge, coulomb of charge. Okay. Now, the potential difference can be measured by the work that is done to move a charge or by the work that the charge can do because of its position in the magnetic field. So those are the last three topics that we were in 6.1. Okay, I won't go back and list all of them, but that was where we left off before. Let's move to 6.2. Okay? 6.2 is basically talking about electric current. What is current, by the way? What is current? The movement of charge. Those coulombs of charge, and it takes a ton and a half, an awful lot of electrons to move to make 1 coulomb, like 10 to the, 18 or something like that, electrons to make 1 coulomb of charge, okay? and how many of those charges move per second. So what your electric current is, and the symbol for electric current, by the way, is I. Where that came from, I have no clue. I is equal to Q, that's charge per unit time. The time rate of change of charge. And if you think back, the very first thing we did was we had a distance or a displacement. Time rate of change of that was the speed or velocity. Then the time rate of change of velocity was acceleration. Time rate of change of momentum, that was force. Time rate of change, we do time rate of change of work, that's power. We were doing time rates of change everywhere. Here we'll do the time rate of change of charge, and that's current. How many charges move through the line in a given time per second? Okay?
Quick question. Would that be a place where you could put one of those triangles or circles?
Yes, it would be a great place for that. Okay? And if you did the triangle or circle here, you put your Q on top, and you put your I and T down here. The charge is equal to the current times time. Current is equal to charge divided by time. Time is equal to charge divided by current. Or circle either one.
The Q is the charge.
The Q is charge, and it goes on top because it's in the numerator there. Okay? Good point. Okay? You could have done the same thing with the last one we had too. When you had voltage is equal work per unit charge, work's on top, volts, and charge on the bottom. Okay? So yeah, you can set up these triangles anytime that's multiplication or division. Okay? Now, what are the units? What was the unit for charge? We just had it. Unit for charge? Second? I couldn't hear. I still can't hear.
I'm sorry, I don't know my batteries for that. What is it?
Okay, what
What are the units?
Unit for charge is, did you say watts?
Watts. V-O-L-T.
No, volts. That's potential difference. What was the unit for charge?
Okay.
We just had it. Named after the French guy whose first name was Charles. Coulomb. Just had it. Q was Coulomb. Okay, so this is Coulomb. What is the unit for current? Another French physicist. Say again?
What you said earlier was joules per coulomb.
Joules per Coulomb, that's a volt. This is coulombs per time, coulombs per second. Time is in seconds. That gives you what is current measured in. Y'all know?
Amps.
Amps, exactly. The unit for Coulomb, for charge is Coulomb. The unit for current is amp. The unit for time is seconds. An amp is a Coulomb per second. A Coulomb is an amp second. Okay? A second could be called a Coulomb per amp, but that's a weird way to say it. Okay? That's what electric current is. The time rate of change of charge. The amount of charge that you're moving. Okay? And we often talk about it in terms of flow of charge. Okay? Now, and we did this in the last lab. We talked about electric circuits. And I thought we had the same model that we described. I believe this was earlier in the slideshow, and it's showing up now in the text. And that was the water model. Okay? Remember, you had two containers of water here. Okay? You had water in here, and you had a pump down here. And the pump pumped the water up to a higher reservoir, giving it potential energy, gravitational potential energy. And then the water came out of here and turned the paddle wheel down here, okay? And turning the paddle wheel, you did work, okay? And we liken the pipes here to the wires, right? We liken the pump to the battery. And we liken the paddle wheel to the light bulb, or whatever was using that energy. The pump gives the water potential energy. The battery gives the charges electric potential energy. Volts, energy per unit charge, joules per coulomb. Okay? The amount of charge that flows through the pipes, that would be like your current. Okay? Water currents, electric currents. They use the same terminology. Okay? That's a pretty ugly picture, but if you got your book, there's a little bit better looking picture there. Okay? Now, sure, this moves the water, but really what's doing the work is the energy the water has. This water down here is just water, and the water in the pipes is just water. Yeah, you have flow of the water, but it's when the pump gives the water more potential energy, that potential energy is what turns the wheel. You might say, well, it's the water turning the wheel. No, it's the energy from the water doing work on the wheel. Same thing is true for your electric currents. It's not the coulombs, the charges, that are doing the work. It's the energy that battery or that generator gives to those charges that does the work. Okay? Energy, work, those are the same thing. Charges, coulombs, water, those are not things that do work. It's the energy that does work. Okay? Now, I wish we had the slide set. I'm not going to draw the battery because I don't draw well. So I'm going to draw the symbol for a battery. Okay? Remember from lab? That's a battery. You want to give it some number of volts? What you want it to be? 5 volts? Okay. We'll make it a 5-volt battery. It's sort of an unusual size, but it's okay. What does that mean? It's giving the charges 5 joules for every charge. 5 joules of energy for every charge. It goes along here and hits the light bulb. Okay, there's your light bulb. The light bulb doesn't use up the charges. No, the charges are not used. It's the energy from the charge that's being used. So whereas the battery pumps up the volts, plus 5 volts here to minus there, the light bulb drops the charge. And if that's the only thing on the circuit, it will drop the charge by, not the charge, the voltage by 5 volts there. Plus 5 going this way, minus 5 going that way. Okay? If the current is flowing in that direction. Okay? And that's your current, by the way, I. And I think I snuck that in on you on the lab, even though we hadn't hit it until today. Okay. Now, sometimes that potential difference, and it has a couple of different names. Remember, the voltage is potential difference. That's the best name for it. Potential difference. Now, sometimes that will be called E. I don't like using E. That's from an old term that we called EMF. And that stood for electromotive force, which they thought described it pretty well. It really doesn't, because it's not a force. It's an energy per unit charge. So EMF, they don't even say electromotive force anymore. They call it EMF, and they'll sometimes say E. So sometimes instead of V, they'll use the symbol E. I don't like that because we usually use capital E to represent energy. So just too many terms using the same letters, not good. That's why they've gone to using V rather than E. But you'll sometimes see that. Okay? So that's the electrical energy source. Okay. So to write that same thing in terms of the units, this is your formula. And in terms of units, it's amps is equal to coulombs per second. And 1 amp is a coulomb per second. Okay. Now, the amp was named after, is it Louis? I think it was, Ampere. French physicist Ampere. So actually, the correct name for the unit is ampere. That's why it's capitalized, because it's named after somebody. But of course, everybody calls it amps. Okay? They just shorten it. This abbreviation, a nickname for ampere is an amp. And that's what we usually use.
Amperes was the guy's name.
Yeah, ampere was the guy's name. So technically the unit is an ampere, but we usually just shorten it and call it an amp.
Well, they still call them amperes too.
Yeah, and they still do. Yeah, it can be called that. And the capital A stands for either one of those. Okay. Now, what's the nature of the current? That's the sort of the next thing we talk about here. And there we have sort of a little problem. Okay. Thank Benjamin Franklin for this problem. Okay. Here was our water model. We'll be through with that. That was such an ugly picture anyway. Okay. I probably could have left that on there. But I'll even take off my current and these things here. I may bring them back later. And we'll even do away with the triangle here. But let's focus now. Oops, I took off too much. Focus on our current. And this we did in lab last time too, if you recall. This was my current here. That's what the arrow. That is called the conventional current. Okay, that's what we usually refer to as the conventional current. And here's why. Everything in physics moves from high potential to low potential. So that's where our conventional current lies. Okay? So here's the problem, folks. What are our usual charge carriers? I say usual because they're not strictly. What's usually carrying the charge? The electrons. But the electrons are negatively charged. Thank you, Benjamin Franklin, for screwing this up. No, he didn't really do it. And of course, the electron would travel from negative to positive. That's the only way they could travel, because they're repelled by the negative pole, attracted to the positive pole. And that's why we say the electron current goes in this direction. Okay? In reality, it really doesn't matter. We can imagine, because we can't see the things anyway, we can imagine the conventional current be the motion that a positive charge would take if it were a positive charge. Of course, we know it's not. But the thing is, it's not really electrons carrying on everything anyway. It's the field that carries it on. The field is what's producing the results for you, not the actual charge carriers themselves. Now, inside the battery, it's not just electrons moving. Inside the battery, you have, what is inside a battery? A car battery, for instance.
Lead acid.
Yes, exactly. You nailed it. Sulfuric acid, right? And that sulfuric acid dissolves lead. So you have positive lead ions moving in one direction and negative sulfate ions moving in the opposite direction. So inside the battery, that's what sets up the potential difference, because you have the positive lead ions moving in this way, the negative sulfate ions moving in that direction. That sets up your potential difference, and therefore you give charges the energy they need to do the work. That's what potential difference is, energy per unit charge. Okay? So that's what they were talking about under the nature of current. The conventional current moves in one direction from positive to negative. The electron current moves in the opposite direction. Today, scientists understand the role of electrons in a current, something that was unknown to Franklin. Oh, I'm sorry, here it is. This description has been used by convention ever since Benjamin Franklin first misnamed the charge of an object based on an accumulation or a positive amount of electrical fluid, which really wasn't. It was negatively charged, so unfortunately that occurred. So we can blame Benjamin Franklin for it, but it works out okay. All right. Question of the last paragraph on page 149. What is the nature of electric current? Okay. Well, it is the movement of charge in some respect, but it's mostly the change of the field. That's what is really what we're measuring, because the current is instantaneous because the field hits everywhere in the circuit at the same time, or very close to the same time. The electric field travels through the conductor at nearly the speed of light as it is established, and that electric field then moves all the charges throughout the circuit instantaneously at the same time. I don't know if any of you are at all familiar with what they call close order drill, say in ROTC or marching, stuff like this. When the unit is supposed to go, everyone goes at the same time. You know, at a stop sign or a stop light, when the light changes, the first car moves, the second car waits a little while, it moves, and then the other. That's not what electrons do. Electrons should be like close order drill. When the commander says, march, everybody takes that first step at the same time, and everything moves, because the field directs it to do that. You don't wait for one charge to move and then another charge to move. That's not the model at all. Okay. Now, what I was talking about in what actually is happening here, and again, this won't be projected and won't be saved on the PowerPoint, but if you got your book and are listening to this, turn to page 150. This is the figure on page 150. You have in the conductor positive charges and negative charges. Now, the negative charges are what move. The positive charges are basically fixed in place. But you have both charges there. So when an electron starts moving, it's attracted to the positive charges. So it tends to go in the direction of more positive charges, right? But as it goes toward a positive charge, it may collide with it. And then it slows down. It may bounce backwards. It goes all sorts of places. And basically what they show here is a very tortuous path. They show this always moving forward, but frankly, they're not moving forward. They're moving all over the place, okay? Sometimes bouncing back, but always tend to be moving forward. That's why the actual motion of charge, that's not what's carrying the work. The work is the energy that those charges have. And in the car example that I was giving you earlier, that's the top of page 151, the battery is located most of the time in the front of the vehicle. Your brake light, of course, is at the very end of the vehicle. They give this, and what they call it is the electron drift velocity. And that's about, believe it or not, 0.01 centimeters per second. Okay? Let me pull back out my pennies. Okay? That penny is about 1 millimeter thick. That would be 1/10 of a centimeter. Okay? How far does an electron travel in a second? Slice that penny into 10 equal slices. That would be the distance an electron would move in a second, on average. Not very far. So, if that's the average drift velocity, if you waited for that electron to get to the taillight from the battery, it would take more than 5 hours, 5.6 hours approximately, for that electron to move they estimate 2 meters of wire going from the front to the back. You don't wait for electrons to move. You wait for the field to move, which is almost instantaneously, almost the speed of light. Okay? Said it dozens of times now. I hope you got it. Now, that would be in a direct current when the electrons tend to be moving in one direction. Okay? The conventional current in this direction, electrons in that direction. They tend to move, but they're bumping into the other particles in the wire. They're doing all sorts of mess in here. It takes forever for it to get there. The field, once you connect the switch, is instantaneous. Okay. Alternating current, on the other hand, the electrons are just going back and forth and back and forth and back and forth and back and forth about, 60 times a second. So they're really not moving very far at all or very fast at all. Okay, they may be fairly fast, but not very far. but it's the field that's set up instantaneously, so all those. So the electrons up there in the lights are just doing like this, okay? Giving their energy to the phosphorescent material that's in there. They picked it up from the capacitors that are in the ballast, okay? That's what's creating. It's not the motion of the electrons. It's the energy of the electrons, okay? So the alternating current, the electrons alternate one way or another and simply move back and forth. No electron drift at all, okay? They just stay in one general location, not moving very fast, but changing fields very, very rapidly. There is a myths and mistakes and misunderstanding blurb at the top of page 151, right-hand column. It's a misunderstanding that electricity is electrons moving through wires at nearly the speed of light. They don't. They move incredibly slowly, okay? It's the field that sets up at nearly the speed of light. So there they say it again. All right, now what we're going to be using in today's lab, and it's just barely getting time to do it, is electrical resistance. Now, like I showed in the earlier thing that I had up here, the electrons meet a lot of obstacles in their path, okay? That means the wire itself, and wires are great conductors, but they still have some type of resistance to the motion of the charges. And that's called electrical resistance. Even the very best of conductors, not superconductors, the best of regular conductors, copper wire, silver, whatever, there's always some resistance, always some line loss, okay? And the guy who studied this was a guy called Georg, which is sort of like our George, except it doesn't have the E at the end, Georg Ohm, a German physicist who discovered the relationship between, and what he was doing, basically, he was applying a voltage to a circuit, measuring the amps that came out of that, the movement of charge, and he found that that they were proportional to each other. Increase the voltage, you increase the amperage. Decrease the voltage, you decrease the amperage. So there was some sort of constant, a proportionality constant. Remember when we did that way early in chapter 1? Well, guess what that proportionality constant is? That is your resistance. So here your formula, V is equal to I times R, where R is this potential, is that a proportionality constant there. Okay? That was what he named it. And they gave it a unit. It's called the resistance. And what is the unit for resistance? Ohm, exactly. So in this thing, volts is equal to ohm times amps. Okay? This is the parameter V, that's the unit V. Don't get them confused. They look just like each other. Okay? Now, can anyone give me another way to write Ohm's law? This, by the way, is one form of Ohm's law. Can anyone give me another way to write it? R is equal to V over I. Not VI, V over I. Okay? And here we can use your circle or your triangle again. And here the V goes on top and the I and the R go on the bottom. Okay? That's Ohm's law. Okay? V is equal to IR. R is equal to V over I. And what's the third one? I is equal to V over R. Exactly. Okay? 3 different equations all represent Ohm's law. Okay? So, what would we named the unit of resistance? Ohm, after good old Georg Ohm. Okay? So, his name was OHM. So what should be the unit for the resistance? Ohm. What would be the symbol for that? Okay. You would think it would be capital O. But what if you had 5 ohms of resistance? What's the problem? Yeah, that looks like a number 50. So no, let's not use the letter O. Not use that. Okay, so erase that. Okay. Well, they went to the Greek alphabet. And in the Greek alphabet, the letter corresponding to our O is Omicron, okay? But it is the letter O, okay? Can't use that either. It still looks like 50. But in the Greek alphabet, there's actually two letters that start with the letter O. The first is one that corresponds to O, Omicron. The other one is the one at the very end of the Greek alphabet. We don't have anything like it in our alphabet, and that is your omega. And that's why they use that Greek symbol for the ohm, because it doesn't look like an O. And that's a capital, because the little omega doesn't look anything like that. Little omega is like this, looks like a W. Not what we use, because it's named after someone, so they use the capital omega. So that would be 5 ohms. Okay? All right. Any questions on Ohm's law? That's what today's lab is about. Just barely got there in time. Okay? So an ohm is to go with the units. If you did the same thing with the units, this would be an ohm is a volt per amp. Or a volt is an ohm amp. Amp ohm, okay? Or an amp is a volt per ohm, okay? Say it any way you want to, okay, as long as you say it right. That's called Ohm's law. All three of those equations. V is equal to I times R, I is equal to V over R, or R is equal to V over I. All expressions of Ohm's law. Okay. I think we have time. Let's try to get this last thing in before we stop. And that's the different features that will determine your resistance. Okay? One thing, and we've talked about it before, is the material. What's the best conductor we have? Not quite. Similar, though.
Copper is...
Okay, copper is almost the best. The best is silver. The very best conductor is silver. Why don't we use silver in our wires rather than copper? Yeah, way too expensive. That's one reason. The second reason is silver tends to be brittle, whereas copper is, you can bend copper and not break it, right? So we use copper. And the difference between silver and copper is really, really small. Silver's better, but not by much. Next down the list is usually listed, no, not quite, almost there, is aluminum. Aluminum's pretty good, but not nearly as good. Copper and silver are like this. Aluminum's way down here, okay, not nearly as good as either one. And actually, during World War II, we were arming the world, including our own military, and we were using a lot of brass in the armament. Does anyone know why we use brass?
Shell casing.
Shell casings, exactly. Why do we use brass, though? Brass is non-magnetic. So if you brought a magnetic field close by, you wouldn't transmit that, and you wouldn't have bombs going off, not intending them to go off, okay?
I was thinking about a box of non-brass casings. You'd have to pick them all up.
Right. Okay. So, and anytime you did that, you're producing an electric field. You don't want an electric field around weapons. So, brass is actually an alloy of copper, I believe steel, and probably zinc, or I believe it's zinc. But copper is a big ingredient in it. Well, guess what? We were using so much brass in World War II, producing so much ammunition, casings and everything else, that copper, the government started controlling the whole supply of copper. So when people were trying to build houses, they couldn't get the wiring for it because it was way too expensive, and they couldn't get it because the government wanted all the copper they could lay their hands on. So people went to the next best, which was aluminum. Aluminum is also somewhat bendable, and stuff like that. But you don't see many houses with aluminum wiring anymore. Does anyone know why?
It's not as good.
It's not as good, exactly. Has greater resistance. So most of those houses that did have aluminum wiring have either burned down because the wire's overheated,
Yeah, I think a lot of
yeah, or they retrofitted.
fifties,
They went back.
they used a lot of it in aluminum, and then they realized
Yeah. Okay.
it
Yeah.
wasn't as good.
Yeah. It was not as good. They either burned down or they
I think
replaced
you
the
can
wire.
still use it, okay?
Who does?
I think you can still use it in certain circumstances.
Okay, possibly, but
I don't
code,
know.
electrical code does not. They frown on it pretty badly. Okay, so yeah, so it's generally not done. Okay, so there's one. The material. Different materials have different resistivities. Okay.
The size of the material.
The second thing is length. That affects resistance. Now think of the water model again. If you had what my grandmother used to call a hose pipe, but it's a hose, okay, and you link a hose to another hose to another hose to another hose, turn on the spigot somewhere way up there, what you get out of it? Just a little dribble, okay? Whereas one hose, water comes spewing out. Because the more hose you got there, the more resistance it has, and the slower the flow of water. Okay? Try it sometime. We were trying to burn some brush piles left over from an ice storm, and we hooked hose to hose to hose to hose to help to it. The water just trickled out. We couldn't put out any fire whatsoever with that. So it was
You
just
find that out after you started the fire.
after we started the fire, and we had, that was a bad story. Okay, but anyway, the length of the conductor, or the length of the transmitter of the electricity, that affects. The longer it is, the more resistance you have. The next thing is the diameter. Okay, the area through which it travels. Think about this. Have you ever gone to one of the fast food places and got a hot cup of coffee in the morning, got one of those little swizzle sticks to stir it, and you can suck the coffee out through that because it's so hot, you want it to cool off as much as possible, right? Okay, try drinking a milkshake through one of those little swizzle sticks. You'll pop your eardrum trying to suck it because it just won't move. The smaller the diameter, the more resistance you have. Same thing with a very thin hose or a straw or anything else. The smaller the diameter, the more resistance you have. Okay? And then the one other thing that affects it, and that is temperature. The higher the temperature, the more resistance. Because at higher temperatures, think about it. Those electrons and the other molecules and everything is bouncing around faster because they have more kinetic energy. And then when the electrons are trying to make their way, or the charge carriers are trying to make their way through, they collide and they have more resistance that way. So those are the four issues. The material, the length of the material, the diameter of the material, and the temperature of the material. And all four of those you have probably witnessed. I guess y'all are old enough to remember those old things we called incandescent light bulbs. Okay, you remember those, right? Nowadays they don't have many of them left, okay? But what is in the incandescent light bulb? What makes the light come on? A filament. Okay, now describe something about that filament. Yes, it is. The diameter, the surface area is tiny. It's like about, if I have some hair,
It's thicker than that.
okay, it would be about the thickness of a hair. Okay, that's a really small diameter, so it's going to have a lot of resistance. Now describe something else about that filament. Is it usually copper? No. Copper conducts it too well. So they use another metal. And most of the time, in the old days, the one that Thomas Edison used when he finally got it to work, well, I believe was tungsten. Much higher resistance than copper. So it's going to, because what makes a light bulb come on anyway? It gets so hot it glows. And that's the other thing about tungsten. It glows a white light, okay, which is what we're used to. Okay? So we had a different material, tungsten, a higher resistance there. Okay? Very small diameter, higher resistance there. But how is that filament, describe that filament You've had some light bulbs that are clear ones. You can see the filament. Tell me something about that filament. Is it in a coil? Yeah. A very, very tight coil. If you stretch that thing out, the length of that filament would be quite long. So there you have your different material, tungsten, higher resistance, different diameter, area, higher resistance, longer length, more resistance. How does temperature come into play? Have you ever had an incandescent light bulb go out on you? When does it usually happen? When does that bulb usually blow? Think about it when you have them go out.
Short circuit.
Second?
Short circuit.
A short circuit. Well, that certainly would make it do, but when does it usually go out?
When does it go out?
Second? Okay, it could do that for sure. Okay, but most of the time with me, when it goes out, is when I first hit the switch. Is that not your experience?
Oh yeah, all the time.
All the time. It's seldom I've been sitting there reading a book and then suddenly the light goes out. I guess it could happen, but most of the time it's when
I
you.
got some bulbs I leave on all the time.
Yeah.
It'll go out about after 2 weeks.
Oh yeah, of course. Yes, it will. Of course, that will. But most of the time, if the light bulb's on and off, it's right when you turn it on, it pops. Okay? Now, why is that?
Surge power, energy.
And why is that? Because the light, the filament is cold when you first turn it on. So it conducts more electricity. Its resistance is lower, so it surges the electricity. You're absolutely right. And if that filament was getting thin because it's been burned so long, then that's when it's going to blow. Okay? And once it gets hot, the resistance is greater, less current goes through. So it will be less likely to blow unless you just wear it out by leaving it on all the time. That's exactly right. Okay, we run out of time, unfortunately. I had hoped to, but didn't quite make it, get to do example 6.3. We'll do that next time. Okay? Sorry that the PowerPoint went out, and I don't know what the problem is. But anyway, I'm going to turn this off